So I wanted to pick up today with our second discussion of sort of the theory of NMR spectroscopy, how NMR spectroscopy works. And let's see, I have something in the chat window already. Mercy, please. Promise, and you'll have plenty of time. All right, so I wanted to give my very simple sort of view of an NMR spectrometer and then return to our discussion last time where we talked about this very minuscule difference between the alpha states and the beta states, and I wanted difference in energy, and I wanted to return to it. So just as I've given my oversimplified drawing of an IR spectrophotometer, I want to give my sort of oversimplified drawing of an NMR spectrometer. And so let's just say you have your sample in a tube. And you put that tube into a magnet, and I'm just going to draw the solenoid sort of like this. And that magnet has to generate an incredibly uniform magnetic field. In other words, that magnetic field needs to differ by well under a part in a million, more like a part in a billion magnetic homogeneity from the bottom of the tube to the top of the tube, from the left of the tube to the right of the tube. And although we're not going to get into technical details in the course, when you're shimming the NMR spectrometer, you're using little additional electromagnets to help to maximize the homogeneity of the magnetic field. The Z shims, the Z1 and Z2 shim, are along what we'll call the Z axis. So we'll call this the Z axis, and we'll just call this the X and Y axis in this plane. And then the X and Y shims make it magnetically homogeneous in the XY plane, and you typically just adjust the Z shims to maximize that homogeneity across the sample. The NMR spectrometer has an RF coil. And again, this is a little bit of a simplification. The coil is wound around a glass tube that surrounds the sample tube. And that RF coil then is connected to an amplifier. And you're going to do two things with that amplifier. You're going to be using that to send an RF pulse to the sample and also to record the signal. And the signal is going to come out as a varying voltage that we're going to see in a moment, or at least see a sketch of. And then because everything is digitally processed in a modern NMR, that's going to go to an analog to digital converter that basically converts that signal into bits, where maybe 1 volt is 2 to the 8th, and half of a volt is 2 to the 7th, and 1/4 of a volt is 2 to the 6th. And the analog to digital converter goes to a computer and to a printer and so forth, and you get your spectrum. So that's sort of the mechanics of the machine. And I guess the one thing that I'll say here is if we've set up our XYZ coordinate this way, the magnetic field is aligned along the Z axis. And that kind of makes sense because your solenoid is filled with liquid helium to bathe the superconducting coil. And then there's a vacuum chamber around that, a dewar, and then there's a layer of liquid nitrogen, and then another vacuum chamber or dewar around that. so that we keep the solenoid very, very cold so it's superconducting. And so the liquid helium and the liquid nitrogen stay at the bottom of the chamber. That magnet is almost invariably run along the z-axis. Maybe one exception would be MRI, magnetic resonance imaging, where that magnet has to be sideways so a person can be put in horizontally into the NMR magnet, into the MRI machine. But anyway, for all the research instruments, for all the laboratory NMR, this is the basic configuration of the NMR spectrometer. All right, that kind of sets the stage for what I'm going to talk about, where we're going to use a little bit of a coordinate system. And so where I left us off last time, there's a very small energy difference between the alpha state, that delta E difference in energy between the alpha state. Remember, that was the state where your spin was aligned with the applied magnetic field, and the beta state. And to give you an idea, we talked before about the energy. We said it is a fraction of a calorie per mole, not a kilocalorie per mole. So this sets up a situation where we actually do have a Boltzmann population of both the alpha and beta states, and we get a Boltzmann distribution. This is different, say, from electronic excitation, where with that 100-ish kilocalorie per mole gap between the ground state and the excited state, all of the molecules are in the ground state. Here we're going to see it's a very small differential. So if we look at, and don't worry about all the math here, because I'm just doing this for demonstration purposes. If we go back to our Boltzmann equation, N beta over N alpha, the difference in equilibrium population of the alpha and beta states is e to the negative delta E over KT, where K is the Boltzmann distribution and T is the temperature. And we've already said delta E is the energy of a photon, a radio wave photon, a photon at 300 or 500 magnetic megahertz. So on your electromagnetic spectrum, where you go from gamma rays to UV to visible to infrared to microwaves to radio waves, on that electromagnetic spectrum, we're down in the radio wave range, and that E equals Planck's constant times nu, and that's equal to Planck's constant times gamma, the magnetogyric ratio, times the applied magnetic field over 2 pi. And so I'm just going to plug and chug here. Don't worry about all the calculations, and I've chosen the units so that they work out together. So at 75,000 Gauss, remember we said that was a 300 megahertz NMR, so it's sort of a middle of the road or low end NMR spectrometer these days. And let's just take room temperature. And so I'll say in 298 K, if we plug and chug here, N alpha or N beta over N alpha equals E to the negative delta H gamma B naught divided by 2 pi, all divided by KT. And then I'll put in some numbers. For Planck's constant, it's 6.63 times 10 to the negative 34. So E to the negative 6.63 times 10 to the negative 34. Again, don't stress over the math here. Times 26753. Remember, that was the magnetogyric ratio for a proton. And I said we're at 70,500 Gauss. And I'm going to divide that by 2 pi. I'm not going to put in the number. And then we need to throw in our Boltzmann constant, 1.38 times 10 to the negative 23rd in the denominator. And I said we're at 298 K. So if we work through all of that mathematics, we end up with the following. And I think I'll start us on a fresh page here, just so I'm not stooping down. I'll leave that equation up for at least a moment so you can copy it. All right, so if we start on a fresh page here, work through the math, what we get is n beta divided by n alpha for this situation of a 300 megahertz NMR and a proton equals 0.99952. In other words, a very small number of molecules less are in the beta state than the alpha state. And maybe the easiest way for me to explain this clearly is to put this number as a quotient of 999,952 divided by 1 million, just to make things painfully clear. To put another way, out of almost 2 million molecules or 2 million protons, we have roughly 48 protons more in the alpha state out of 2 million. I'll say tilde 2 million, since I'm rounding the sum of 1,999,952. I'm rounding that to 2 million. That's a very small difference. And again, I contrast that with the ground state and excited state for either the UV, vis, or the IR, where virtually all molecules, or we'll just say all molecules, are in the ground state. So they're all available to absorb a photon. Whereas here, of our nuclei, only that small differential population is available to absorb a photon, because for the higher energy state, you will excite them to emit a photon. In other words, it's not just that the lower ones can jump to the higher state absorbing a photon, but you can stimulate emission on the other one. Well, before we get on with that, I just want to explain why bigger is better. So let's go ahead and say for 117,500 Gauss magnet, so that's our 500 megahertz NMR. In other words, a good, nice sort of, nice NMR. N beta divided by N alpha now is 0.99919, or again, to put it in this way, out of 2 million, 81 protons more in the alpha state out of approximately 2. Questions or thoughts here?
Yeah, I got one regarding like why we need a slight excess in the alpha state. I'm a little bit confused with what you were saying about why we need the excess, because I was kind of thinking if you had like a 50-50 split in the N alpha or N beta, if you just shine the right wavelength of light on it, you would be able to populate a higher state and you would see the absorption.
But it's equal. So let us pretend for a moment, and I'm going to represent this with 5 nuclei rather than drawing out 2 million nuclei, since I can't draw 2 million. So let's look at this case here, where here's our difference in energy, and here's our beta state, and here's our alpha state. And imagine that you have a photon at the right wavelength, in other words, a radio wave photon. If the photon interacts with these nuclei, you will have an equal probability of exciting this nuclei to the excited nucleus to the excited state, or kicking this nucleus down to the lower state. In other words, you will have an equal probability of excitation and absorption of a photon, or stimulation and emission of a photon. And so the result will be no net absorbance of photons. And this is the damning thing about it. One of the damning things about NMR spectroscopy is that we are wholly dependent on this teeny tiny differential in population between alpha and beta states. And the only easy way, easy being a caveat, the only easy way to increase that difference in population, and again, I'm going to cartoon this not with 2 million nuclei, but with 10 nuclei. The only easy way to increase that teeny tiny differential, and so I'll represent that teeny tiny differential as 6 in the alpha state and 4 in the beta state. The only easy way to increase this differential is to increase our field strength, and we are limited by the strength of the magnets that can be developed, where really that limit has been roughly a gigahertz, and even that is very hard to achieve homogeneously. And for a while there, we were growing. Now we've pretty much capped out. A few research instruments are being pushed higher. And in fact, an interesting trend is that a lot of schools have actually given up their highest field NMR spectrometers and sent them to the scrap heap because they've been too expensive to maintain. They use a lot of liquid helium. They actually, we on our 800 pump that liquid helium. So instead of just being at 4 degrees Kelvin, we have to go down to about 2 degrees Kelvin to pump as much current as we can through the solenoid. So basically, by pulling a vacuum and evaporating the liquid helium, it gets even colder than 4 Kelvin, and the solenoid, the superconducting solenoid, is able to take more electricity. So we're really damned. Now, the one exception is hyperpolarization, and this is a technique that's come into play in carbon-13 NMR more than proton NMR, and also in some biomedical imaging with xenon, where by using various tricks, you can swap the Boltzmann population of another species. So in hyperpolarization, what's done is you end up swapping. So in free radicals, you also can have spin up and spin down, and they're of an electron. And because the energy gaps are now bigger, instead of being in the radio frequency range, the absorption's in the microwave, frequency range. So delta E is bigger. So the Boltzmann distribution is bigger. By hyperpolarization, you can swap that and end up tricking nature. So if I were drawing this, I'd maybe draw 8 in the ground state or 7 in the ground state and 3 in the higher energy beta state. But that's an unusual trick. We will, by the way, when we come to carbon NMR, though, we're going to learn, and particularly when we come to 2D NMR and inverse detection, we're going to learn how we do that with the carbon nucleus using protons. Because remember, I said with the magnetogyric ratio of carbon, it's about 1/4 the magnetogyric ratio of protons. So the difference between the beta state and alpha state for C13, that difference in energy is about 1/4 as big, and the difference in Boltzmann population is even smaller. So carbon is damned again and again and again. It's damned by the 1% isotopic abundance of C13. It's damned by the lower magnetogyric ratio and hence the lower Boltzmann population. And we're going to see 2 more damning factors in the rate of precession and the size of the nuclear vector. So I don't know if that answers questions, but it's actually sort of a relevant segue into the rest of today's lesson. Other questions, because this is good. This is a good time to talk.
Can we see your cat?
Baral, she doesn't come when called. Come on, Baral. Come on. She doesn't like to be picked up.
Okay, that's fine. I'm just so curious. I always hear.
I will see if I can bring her. And if anyone wants to give her a gift, she likes the 1A7 boxes from Amazon. They're the size of a big shoebox, and she likes to sit in them. So the only way she tolerates being picked up without objecting is if she gets in her 1A7 box, and then I can pick her up and carry her around. And up the stairs she goes, meowing her fool head off. She is a Bengal cat, which is a little bit of a strange breed of cat, which makes her a little more wild and so forth.
Is it something like this?
That's a A1 box, 1A7, but don't stress too much. I get a ton of stuff from Amazon. I'm sure I'll have another one as her box is breaking down. All right. So I want to come back to our NMR spectrometer, and I'll set up our little axes, which we're going to use for the next discussion. So here's my cartoon of the RF coil. Here's our z-axis. I'm not going to draw the solenoid, and we're just going to remember that here's our applied magnetic field. And at this point, we're going to think about that small differential population of nuclei in the alpha state aligned with the applied magnetic field. Because if for every nucleus you have a spin up, you have another one that's spin down, they'll cancel each other. There'll be no net magnetization. But remember, I said there's 81 out of 2 million pointing up more than the numbers pointing down here. So we're going to focus on that small differential population. And much like a gyroscope, so I'm going to go ahead and sort of represent 2 of them, but they're going to be all like this, much like a gyroscope hanging on a string. They don't point quite up, but they point off on a little angle, and they precess. So if you've ever hung a gyroscope on a rope, it's a lot of fun on a little string. It sort of spins off axis, and it doesn't just hang vertically, it hangs a little bit off axis, and then it moves around. It's a lot of fun to look at. That's called precession. of, I'll say, our differential population of spins. And in this case, you'll notice you have a net magnetization along the z-axis. In other words, the vector sum of this vector and all the other vectors pointing in all the other directions is directly upwards. It's not in the xy plane. But what happens to our net magnetization, so this is our net magnetization here, is when we apply an RF pulse, much like the right-hand rule in physics, when we apply a RF pulse, we drag that down into the xy plane. In other words, that net magnetization goes from pointing up. We've applied effectively a force to it, forced it down into the XY plane. In other words, it is now along the y-axis. If our coil is on the x-axis. Does that make sense in terms of what we've learned in physics back in college or even high school? Go ahead.
Yes, specifically the RF pulse we're hitting it with is negative X.
Technically, positive X over here as I've drawn it. Am I right? I think I'm right on my right hand. I think I'm right on my right hand rule.
Yeah, it's okay.
Now, the reality is a little more complicated. So you're going to learn, any of you who's run an NMR spectrometer probably knows that you don't just collect a single scan. You usually collect them in groups of 4 in order to get signal averaging. So we'll do 4 scans, 8 scans, 64 scans, or so forth in multiples of 4. Because in reality, what's done in order to minimize noise and maximize artifacts and maximize signal is called phase cycling, where the reality is we apply a pulse along the x-axis, we observe the resulting signal, which I'll tell you about in a moment. Then we apply a pulse along the y-axis and we observe the signal. Then we apply a pulse along the negative x-axis and observe a signal. Then we apply a pulse along the negative y-axis and observe a signal. So most of the experiments that you do will involve phase cycling, and your instructions are going to be choose NS equals 4 or some multiple thereof. And it's for that reason. But again, we're getting a very simplified view of the physics here. Well, I want us to look at this from a second perspective in just a moment, but I should stop for any additional questions. All right, let's look at this view here, which is almost classical physics, right? I was talking about a gyroscope and I was talking about applying a force to a vector. Let's look at it from a more quantum mechanical point of view. When you apply, so here's my little pigeon cartoon of our alpha and beta states with this teeny tiny difference in population. and I'm cartooning it as 6 nuclei pointing up and 4 nuclei pointing down to represent that minuscule difference. When we apply this RF pulse, which I'm going to call a 90-degree pulse, or a pi/2 pulse, pi, that's just radians instead of degrees. What happens is that equalizes the population in the alpha and beta state. So my little pigeon cartoon is now going to go to 5 and 5, 5 up, 5 down, reflecting that small difference. That's what happens. And that's, as I said, you can excite up, but you can also excite down and induce emission. And so this sort of matches to this view in that now there's no net magnetization along the z-axis. We've leveled our population of alpha and beta states. We don't have a net z vector, but because of this sort of right-hand rule, we've gone ahead and now driven our magnetization into the xy plane. And really our limits without hyperpolarization that I mentioned before is we can either do this, or we can go ahead and I'll give the same little pigeon drawing, 6 up, 6 down, 4 down. Here's our beta state. Here's our alpha state. The furthest we can go is 180-degree pulse. We would call that a pi pulse. And that's just a longer pulse. So basically, it's just turning on the amplifier to apply the RF pulse longer or harder. And now we can invert the population. And then we have our net magnetization instead of being in the XY plane. Now our net magnetization is along the negative z-axis. And that's about it. If we apply a still longer pulse, you say, oh, wait, we can trick nature. We just end up driving that vector back up along the negative y-axis. And if we continue, so that would be a 270-degree pulse. If we continue and still apply it longer, we've just applied a 360-degree pulse and we're back where we started. So that's the sort of gist of the spin physics of this quantum view of what's happening here. And we are wholly reliant on this difference in population. Now that essentially has set up our NMR experiment, because the next thing that's going to occur is what happens to those spins in the XY plane after our 90-degree pulse. So after our 90-degree pulse, our net magnetization is in the XY plane, and I'm going to come right back to my little cartoon of my terrible X, Y, and Z axis and my oversimplified cartoon of my RF coil. And now what I'm going to point out is here's our net magnetization. And I already mentioned that that net magnetization, when the spins were up, each of the spins was precessing, but it didn't really matter because there was no net magnetization on the z-axis. Now, when we get precession, remember, that's just your gyroscope spinning around. Now, when we get precession, And that magnetization, my arm, this magnetization vector is along the y-axis. It's rotating like this. And when you have a rotating magnet in an RF coil, what happens?
You get a electric flow of the electricity.
Yeah, go ahead. I'm sorry.
Oh yeah, you get a flow of electricity.
You get a flow of electricity. So now you get a current in the RF coil, a teeny tiny current that depends on the size of this vector, which, as I said, is bigger in a bigger magnetic field and is bigger for a nucleus with a relatively big magnetogyric ratio for a proton. And the rate of precession is occurring at that frequency, that's the excitation frequency, so at 300 megahertz or 500 megahertz. And so what you see in the coil now is a voltage, I'll call it, I'll write voltage, V. And remember, this axis, if you think about it, is sort of time, because in a oscillating signal, we're going to look at voltage as a function of time. And you get a cosine wave where the rate of precession, and thus the frequency, equals the nu for that proton. So you get a cosine wave. And so that signal is going into your amplifier. That signal is going in to the amplifier and then to the analog to digital converter, and giving you a signal that's basically a frequency. And that sets us up for the next step, where I want to try to teach us about a Fourier transform. But let's take some questions at this point.
Okay, so the current induced is dependent on the rate of precession. And what is the rate of precession like based on? Is that like inherent to the molecule, or is it based off the magnetic field? Or
it is the same rate as that energy difference nu. So it depends on the size of the magnetogyric ratio, the size of the size of the magnetic field. So that's going to determine more specifically the frequency, and then the amplitude. So the frequency, in other words, the periodicity, the cycles per second, is going to be 300 megahertz or 500 megahertz, or, as we're going to see, slight differences depending on where the proton is in the molecule. And then the amplitude is going to depend on the difference in population. So if we have 81 more nuclei, and again, I'm just pulling that number out of 2 million, if we have 81 more nuclei in the alpha state than in the beta, or if we have 81 more nuclei in our initial differential Boltzmann population, we will get a bigger amplitude than if we only had 40 nuclei. Furthermore, we're going to, in just a moment, talk about relaxation, where those populations drop. We return our magnetization to the z-axis, and we're going to see in a moment that we don't really have a cosine wave, but we have a cosine wave with a half-life and exponential decay imposed upon it, and that's going to have very real implications. Other questions?
sorry, another one. So this one's kind of like more sanity check. So I just wanted to know if, so the net magnetization depends on the spin populations. Is that,
Net magnetization depends on the differential population.
or differential in spin populations?
Right.
Okay, so what are the other combinations, I guess, of like the differences in spin populations that give like net magnetization in like the YZ plane or the Y-axis or other types?
Well, if we do a pi pulse, so if we do a 180-degree pulse, all our magnetization is now along the negative z-axis, and we get zero differential. We get zero magnetic vector in the xy plane. So we're down to zero signal. Now, in practice, for various reasons, often you're not applying a 90-degree pulse. You're actually applying like a 60-degree pulse or a 30-degree pulse for practical reasons. So often you don't use the full Boltzmann distribution, but we're not going to think that far ahead because that's getting into fine details here.
Okay, thanks.
Anyone else?
Yeah.
Oh, sorry. Go ahead, Brian.
Yeah. So when okay, I think I'm kind of understanding. You know, it makes sense to me when you have the solenoid and the current going. I guess it would be counterclockwise because the right-hand rule, you would have the magnetic field vector would be pointing up in the z direction, and then you shift it so it's pointing in the y direction. So with the I guess I'm a little confused the way you describe the precession when the magnetic field vector is pointing in the y direction. So what would be the direction of the precession? Would it be like around the y-axis?
It'll be around the z-axis. So just as I sort of pantomimed with my body like this, I'm standing on the z-axis. So now the vector's precessing in the xy plane.
I thought it was doing that beforehand.
Well, it is. The nuclei are, but for every nucleus off axis in one direction, there's one and equal and opposite in the other direction. So there's no net magnetization in the xy plane.
Okay, I got it. Okay.
Other questions? All right, at this point, I want to set up a Fourier transform because that is one of the things that I think to many people is sort of a mystery. Certainly it's a mystery to my cat. So let's go to our handout. All right, so this is just me in Excel generating a cosine wave with a 1 cycle per second periodicity. And a Fourier transform is just a mathematical process whereby we go ahead and we convert this frequency domain, this time domain into a frequency domain. So I've sort of emphasized we have seconds here. So when we Fourier transform, now we still get a y-axis that's amplitude, but we get an x-axis that's frequency, and this is in hertz. And so if I have 0 and 1 and 2 and 3, we get a line at 1 hertz. And then over here, again, for the sake of just representation, I've set up a cosine wave that's twice as fast. And so I'm going to again draw my frequency axis. And this time, you can tell me, where do I draw my line? Where do I draw my line?
multiple places, 1, 2, and 3?
What do people think? What's the Fourier transform of a cosine wave at 2 cycles per second?
Oh, 2 then?
2.
2.
2. So that is half the mystery of a Fourier transform. It simply says, how many cycles is the cosine wave? Now, NMR spectroscopy wouldn't be very interesting if all the nuclei are the same. And if you have a molecule of ethanol, you have nuclei in a methyl group, nuclei on a methylene group, and nuclei on a proton, and they all precess at slightly different frequencies. And so you get a gamish of frequencies, which at the simplest level, I have literally just added my cosine wave with periodicity of 1 and my cosine wave with periodicity of 2 cycles per second to generate a sum, which I've shown in red, and then transposed here. And the mystery of the Fourier transform, the mathematical process of a Fourier transform here, really does decompose this line, this curve, into 2 separate lines. So the Fourier transform now gives us a line at 1 cycle per second and 2 cycles per second. And of course, your gamish of frequencies is way more complicated than what you're seeing in my red graph, but that is the first part of a free induction decay. In other words, what you're seeing is a sum of different frequencies. Now, the reality gets a little more complicated, and the next concept I want to introduce is the concept of exponential decay. So I've lied. I've lied just a little bit. I've lied just a little bit in my description of a Fourier transform, because the Fourier transform of a cutoff cosine wave is not really a sharp line. It's a little line with wigglings. But imagine if this goes on to infinity on our time axis. In other words, if it goes on, etc., then you get an infinitely sharp line. But the reality is our magnetization returns to the z-axis or unbunches. And so what you see is not a cosine wave going on forever, but one that's falling off exponentially with a half-life, what we call an exponential decay. And when you Fourier transform that, you get what's called a Lorentzian line shape. Like so. And that is what a peak looks like. Now, actually, it's even a little bit more complicated because typically you still stop your experiment. So typically we will impose an extra exponential decay on here through exponential multiplication. So that is the gist of how you get from this physics of the population of nuclei to an actual difference in population. And I said there's relaxation. There's essentially 2 types of relaxation that occurs. One of them is easier to understand than the other, One of them is called longitudinal relaxation, and that is the return of magnetization to the z-axis. So the relaxation is the fall off of signal with time. So you have what's called longitudinal relaxation, sometimes referred to as spin lattice relaxation. Or T1 relaxation. And that's your re-equilibration of your populations of the alpha and beta states. Through transfer of energy through thermal motions of the sample.
There's your new box for your cat.
Could be. We get a lot of Amazon deliveries around here. So in a cartoon fashion, we could just say, okay, here's our net magnetization. So here's our XYZ axis. We had our net magnetization in the XY plane, but with time, the spins flip. We return to our Boltzmann population, and we end up with our net magnetization back along the z-axis. All good things must come to an end. The second form of relaxation is called transverse relaxation. This one's a little harder to understand. It's also called spin-spin relaxation or T2 relaxation. And spin-spin relaxation involves interaction of the spins with other nuclei. And that's going to lead to unbunching of the spins in the XY plane. And that leads to a loss of magnetization. And I have a lot of trouble trying to represent 3 dimensions in 2, but if you imagine that, of course, we don't have one spin, but we have multiple spins in the XY plane, with time as they're processing, some will lag, some will lead, like my arms in the XY plane here. And I'll represent that like so, where some are going a little more toward the back, some a little more toward the front. And the result, as those multiple spins diverge, the result is less net magnetization in the XY plane. Usually T2 relaxation occurs from things like paramagnetic species like oxygen in the sample that can interact. But the result, either from longitudinal relaxation or transverse relaxation, is a loss of net magnetization. And I think rather than trying to talk about the effect right now on the line width, I think this is probably a good point to stop, take any final questions, and maybe we can pick up with a few last comments on this next time on Friday morning before we start getting into chemical shift. So any last comments or questions before we get on to our next classes?
Is this transverse relaxation somehow related to the kind of like the coupling that we see in HNMR, or is that a different thing?
That is a different thing. And that is, and we're going to get into two concepts. One is chemical shift, which is how the electrons in the molecule affect that applied magnetic field, because all the protons don't feel the exact same magnetic field. The electrons shield the protons, provide opposing magnetic fields. And the more electrons you have nearby, the less the molecules feel, the protons feel the applied magnetic field. So an electronegative atom pulls the electrons away and leaves that proton more naked. So that's chemical shift. And then the spins of other protons in turn get felt through the electrons in the bond, get felt by the proton in question. And that's what gives rise to spin-spin coupling. Honestly, if all of this were all there were to NMR spectroscopy, organic chemists wouldn't have any use for the technique. And in fact, the physicists were the ones who first invented NMR spectroscopy, figuring they would find a universal property of a proton. And when they saw that the chemical environment of the proton affected its exact frequency, they were very disappointed because they thought this isn't pure like physics, it's dirty like chemistry. So they gave this name, this effect, the name chemical shift, a name of contempt. But we chemists took it over, and it's become one of the most useful spectroscopic techniques because it provides such intricate information on the molecule. So that all of this sort of basic physics gets superimposed on what we do. But then for like this unbunching here, when we actually do pulse sequences, there will be times where we apply a negative 180-degree pulse that goes ahead and flips these spins, a pulse in the XY plane that flips these spins so they point in the other direction and bunch back up, and that's called a spin echo. So there's a whole bunch of stuff that gets used in the pulse sequences to offset transverse relaxation, to offset this unbunching of the spins. Other final questions or comments?
If you would like to learn more about the Fourier transform, or you're still curious about it, there's a YouTube video that I think is an excellent description of it. I've posted the link in the chat. Watch at your leisure. It's not required reading. I just think it's interesting.
Cool. Thank you for sharing that, James. All right, well, on this note, I will let you go to your next class. Thank you for bearing with me, and we will pick up next time talking about chemical shift and maybe just a hair on the uncertainty principle and relaxation. Ciao.